today is our last lecture on nonlinear systems. Like I said, nonlinear systems are not on this midterm, but they will be on the final. We have been through various different types of nonlinear systems so far. We've looked at predator-prey models, we've looked at disease models, competition models last time out, and today we're looking at a variation on the competition models and thinking about cooperation instead. So we're going to be doing basically the same stuff that we've done before, thinking about equilibria or fixed points, thinking about their stability and drawing phase planes. There's a pattern here. There's lots of practice for you guys to work on this stuff. Okay, so last time we met a competition model that looked like this, which was basically a logistic model for two species. And then we had this additional term with these coefficients, these alpha 1,2s and alpha 2,1s that were negative terms. So they were indicating that there was a negative interaction between these species, competition in this case. And so we had a look at this and the different types of orientations of phase planes that we could get and what that would mean for the stability of this system. So could these species coexist or not? When could they coexist or not, depending on these values here, as well as their carrying capacities. So that was a model where we had negative interactions. Now we're going to think about what happens if we have a positive interaction here. So what does this mean? So rather than a competition model, we have a cooperation model. So if we just cross out these interspecific interaction terms here, we just have a logistic model for each species. They're independent of each other. But now if we add in these interspecific terms here, because they're positive, what we're saying here is that N2 is having a positive effect on the growth rate of species 1, and N1 is having a positive effect on the growth rate of species 2. So they're cooperating. So there's lots of examples of this. They could be like plants and pollinators, hosts and microbial symbionts, whales and feeder fish, all of these different examples where there's some sort of cooperation between the species. Okay, so the first thing we want to do is we want to find the fixed points, and then we're going to look at the stability. I have a show of hands. Who wants me to go through? I'm going to either go through the fixed points or the stability and leave the rest for you guys to practice, okay? So would you guys, show of hands, who wants me to go through the fixed points and then give you the stability? No one, okay. Who wants me to give you the fixed points and, wait, which way did I go? Let's do that again. Who wants me to work through the fixed points? Let's show of hands. Okay. Who wants me to work through the stability instead? Right, roughly even, that's great. In that case, I will go through the fixed points just to make sure that bit is clear. Obviously, the solutions to all of these things will be online, and I'll go through the phase points as well. So part of the reason I don't want to go through everything is I want to give you guys some more practice as well, so you can do these things in your own time. Okay, so when we're trying to find fixed points, remember what we're doing is we're going to be setting these equations here equal to 0, and they have to both be equal to 0 in order for us to get a fixed point. So let's think about the first one. So if we set dn1 dt equal to 0, that means that either we have n1 equal to 0, because we have these two terms multiplied together. To get 0, 1, or both of them have to equal 0. So you either need n1 to equal 0 or 1 minus n1 plus n2 over 2 to equal 0. We can rearrange this for n1. We should have 1 plus n2 over 2. So n1 is equal to 1 plus n2 over 2. So what this means is we either need this or we need this condition to have dn1 dt equal to 0. What do we do now? Well, one way we can do this is just, let's set dn2 dt equal to 0. And consider what happens if n1 is equal to 0. So this first thing here. So if we have dn2 dt equal to 0 and n1 is equal to 0. Remember, we want both of these things to simultaneously be 0. And above, we've got the conditions for when dn1 dt is equal to 0. So we need to substitute those in. So what do we have here? If n1 is equal to 0, then that means that this term here is 0. And this is just our logistic model. So n2 times by 1 minus n2 must equal 0, which implies that n2 is equal to 1 or n2 is equal to 0. Okay, so for this point, I can keep track of what my fixed points are. So I know that I've got a fixed point at 0, 0, and another one at 0, 1. Okay, now we consider the other condition from the first equation. So now we say if the n2 dt is equal to 0 and n1 is equal to 1 plus n2 over 2, then what do we have? Well, in this case, we need n2 times by 1 minus n2 plus n1 over 2 equals 0. That's just the second equation equal to 0. That means that either n2 is equal to 0, or the bit in the brackets, 1 minus n2 plus n1 over 2 is equal to 0. So again, we've got another fixed point here already. If n1 is equal to 1 plus n2 over 2, then either we need n2 is equal to 0 or the second condition here on the right to be equal to 0. If n2 is equal to 0, we can substitute it back into here. That's going to give me n1 is 1 and n2 is 0. So the final ones, we've got 3 of our fixed points so far. There's a fourth one here. So if we have 1 minus n2 minus n1 over 2 is equal to 0. And remember, we had to start with n1 is equal to 1 plus n2 over 2. We've got 2 equations here and 2 unknowns. We just need to solve these. In fact, this is a linear system. You could put this in a linear system and solve it using matrices like we had previously. So let's rearrange this and substitute this into here. We are going to have, say, we're going to have a 1 minus n2 minus n1 over 2. So stick this half out the front. We're going to have 1 plus n2 over 2. That's going to equal 0. Just span those brackets. 1 minus n2 minus a half minus n2 over 4 is equal to 0. I've got a mistake here. That's because I've got an additional plus. Sorry, I said minus n1 over 2. I'm thinking of my competition model. That should have been a plus n1 over 2 up here, which makes this a plus n1 over 2, which makes this a plus, and this a plus. Sorry about that. I work a lot with competition models, so I don't do cooperation models that much. Okay, so this is a positive interaction, which is why we've had a positive sign here, not a negative sign. Okay, let's see where we're at. So we've got a 1 plus a half, so it's going to be 3 over 2. We've got minus n over 2 plus a quarter of n over 2. So that's going to be minus 3/4 n2, 0. So this just simplifies to be n2 is equal to 2. If n2 is equal to 2, we just substitute it back into this thing up here. So we had 1 minus 2 plus n1 over 2 is equal to 0. We can rearrange to be n1 is equal to 2. So this means that we have 4 equilibria, or 4 fixed points. 0, 0, 1, 0, 0, 1, and 2, 2. You might see these referred to as 0, 0 being a trivial equilibrium. It's trivial because if this is a population model, and if there's no individuals in the population, then obviously nothing's going to change. 1, 0, and 0, 1 are often called semi-trivial equilibria because there's only one species there. So this 2 species model collapses to a 1 species model. It's just the logistic model with 1 species. That's why it's called semi-trivial. And then this last one here is often called a non-trivial or a coexistence equilibrium because both of our species are present. We don't know anything about the stability of that though. Okay. So how do we work out stability? Well, we need to look at our Jacobian. This Jacobian J is a function of n1 and n2. Sometimes we don't put those n1s, n2s in there because it's implied, but I'm just including them there to make sure it's explicit here. And here we're taking our Jacobian as our matrix of partial differentials of our partial derivatives of our functions, dn1 dt and dn2 dt. So for dn1 dt, if we take this partial with respect to n1, we get 1 minus 2n1 plus n2 over 2. If you're in this sort of situation, just before I go on here, and you're not comfortable with taking the derivative when it's in this form, just expand the brackets out. Okay, so if I expand these brackets out, I have an n1 minus n1 squared plus n1 n2 over 2. Likewise, here I'll have an n2 minus n2 squared plus n1 n2 over 2. I think in the solutions I've got a minus here, but that's supposed to be a plus. Hopefully I remember to correct that. Okay, so if you're in this situation, you don't want to calculate your derivatives directly from here, just expand the brackets like I've done there. They're all just power laws here, so they're nice and easy to take the derivatives of. Okay, the second partial with respect to n2 here is going to be just n1 over 2. And this system is symmetric, so I can immediately write down what the other partials are just by changing my n1s and n2s, switching the order of these things around. So in the bottom right, I have 1 minus 2 n2 plus n1 over 2. Okay, so I've got my 4 fixed points. I've got my Jacobian. Now I just need to substitute those fixed points one by one into my Jacobian and either read off my eigenvalues or look at the trace and determinant and then figure out what the stability is. So I want you guys to have a go at doing that for practice. Okay. Just a reminder, I'll put them up on here. Our fixed points were 0, 0, 1, 0, 0, 1, and 2, 2. Okay, let's see how you guys got on. So our first equilibrium was our trivial equilibrium, 0, 0. So at 0, 0, what do we have? Well, we substitute this into our Jacobian. Our Jacobian here. We're going to have all the n1 and n2 terms are going to be 0. So we're just going to be having 1, 0, 0, 1. So we could look at the trace and the determinant here. If I look at the trace, I'm going to have a trace of 1 plus 1, which is 2. That puts me on the right-hand side of this diagram. This is just a sketch of the diagram that I've shared with you guys previously. So we'd have a positive trace and our determinant would also be positive. We could look at our trace squared minus 4 times the determinant to also work out whether we got an unstable spiral or an unstable node. Have an unstable node here. So the other thing we could do is, because this is in diagonal form, so remember, if we have a 0 in this place or in this place, we can immediately read off our eigenvalues. So in this case, one of my eigenvalues is 1, the other one is also 1. So 0, 0 is unstable. If you'd worked out the trace, this would have been 2, the determinant would have been 1. In this case, when we do take the trace squared minus 4 times the determinant, you'd end up with 4 minus 4, which is equal to 0. So this is one of those cases that is on the borderline. This is actually something called a star. So you're actually on this curve here. That is a borderline case here. If this was to appear in an exam, I would just expect you to say it's unstable. Okay. I wouldn't. We won't get into stars. The reason it's a star is because we have these repeated eigenvalues here. That's a bit beyond this course. What I really care about here is whether it's stable or unstable. So in this case, it's unstable. That's all I care about here. Okay. At 0, 1. J at 0, 1 is going to be 1 minus a half, 0, a half, 1 minus 2. J is a half, 0, a half, minus 1. Again, because we've got a 0 up here, we're in lower triangular form this time for our matrix. So that means our eigenvalues here, we can again read them just off elements on the main diagonal. We have lambda 1 is equal to a half, lambda 2 is equal to minus 1. So if you remember what it means for your eigenvalues to be positive and negative, if one of them is positive, one of them is negative, that means you have a saddle. Alternatively, if you work out your trace is going to be equal to a half minus 1, which is less than 0. Your determinant is going to be minus a half minus 0, which is less than 0. So you're in the bottom region of the graph, the diagram over here, you have a saddle. Question, yeah? Let's see. Yes, it should be 3 over 2, I think. I think I just copied that down incorrectly. Oh, I think it's because I started doing the 1, 0 instead. So yes, n1 is 0, and then you add on a half here. So this should be correct. That should be 3 over 2. That doesn't end up changing any of that changed the sign of this, but that doesn't matter. That should be greater than 0. Your eigenvalues here, you have 3 over 2 minus 1. So it doesn't change the stability of anything, but thank you for spotting that. Again, I'm slipping back into my competition models. Okay, so we have 0, 1 as a saddle. Because this system is symmetric, we can also say that 1, 0 is also a saddle. I'm not going to repeat that. You can work that one out if you want, but it's going to be exactly the same, just flipped around because this system is symmetric. Okay, let's think about our coexistence equilibrium. So at 2, 2, Jacobian this time is going to be 1 minus 4 plus 1, 1, 1, and again 1 minus 4 plus 1. It's nice because this is symmetric. So we have minus 2, 1, 1, minus 2. I'm just going to call this J star for convenience. Okay, so We can't just read up our eigenvalues straight away in this case. We have to work out our trace and determinant, or we have to calculate our eigenvalues. The trace and the determinant are easiest to work with. So here our trace is going to be -2 minus 2, which is -4. Our determinant is going to be -2 times by -2 minus 1 times by 1. 4 minus 1 is equal to 3. So you have a negative trace and a positive determinant. So that tells me I'm somewhere up here. Trace squared minus 4 times the determinant. It's going to be -4 squared minus 4 times by 3. 16 minus 12, which is positive. So we have real eigenvalues with a negative trace. So we have a stable node. So it's the equivalent of me being in this region. Okay. Strong hint here, nonlinear systems will appear on the final. Okay, so let's think about our phase plane now. I'm going to work through this one with you guys. So whenever we're working out our phase planes, we need to think about our null lines. But if we've already worked out what our equilibria are, we've already found our null lines, okay? Because we have these conditions for when either of our equations, dm1 dt or dn2 dt, are equal to 0. So we know that n1 is equal to 0 as a null line. Also, n1 is equal to 1 plus n2 over 2 is also a null line. We also know that n2 is equal to 0 is a null line, or this equation here on the right-hand side will also give us a null line. So we already have our null lines. So they are n1 is equal to 0, and we had n1 is equal to 1 plus n2 over 2. I generally, when I'm writing my null lines, try and rearrange them in terms of whatever is on the vertical axis. A few people asked me this at the office hours the other day, and a lot of people got into issues with the gradient of their null lines. Okay, rewrite these things in terms of if you can, in terms of what is on the vertical axis. So in this case, I'm going to write it in terms of n2, which is equal to 2n1 minus 2. My other null lines are n2 is equal to 0. And similarly, I can write n2 is equal to 1 plus n1 over 2 by rearranging this thing here. So just adding n2 to the other side. Okay, so these are my null lines. So I can sketch them on. In population models, you would typically have null lines on the axes. So they're nice and easy to draw. We have two non-zero or two ones that aren't parallel to the axes. So the line n2 is equal to 2n1 minus 2. We know that that will go through 1, 0 down there. That's the point 1, 0. We know that because we know that we have an equilibria on that axis when n1 is equal to 1. What else do we have? We have n2 is equal to 1 plus n1 over 2. So the gradient here is going to be a half, and the intercept is equal to 1. We draw that. So it looks something like that. So we have equilibria whenever we have an intersection between a blue and a red line here. Some tips on drawing phase planes whenever you're drawing them, whether it's for a homework assignment or it's an exam, I've said this before, please make them big so it's easy to see what is going on, give yourself room to draw on everything. Please also, you don't have to do this, but you need to label it somehow. So sorry, you don't have to color code it, but you need to label it somehow. If I've drawn these all as black lines, I need to say that this is, say, the line dn1 dt is equal to 0. And this is the line n2 is equal to 2n1 minus 2. Okay. You need to provide some sort of key to what is going on here. I like to color code it because it helps me remember what are the null clients to my n1 variable and what are the null clients to my n2 variable. You could dash them. That's another way of doing it. Solid and dash lines, it's fine. Just make it clear what is going on by having a key of some kind. Okay, so I've got my core equilibria here. What do we know about? We don't know our direction field, so let's work that out. So here, I'm going to focus on what's going on the axes. On n1 is equal to 0. We know by definition that dn1 dt is equal to 0. What is going on with it, dn2 dt? So typically as well at this point, I like to draw on some horizontal and vertical lines. So I know on my blue null line that I must be moving up and down. I can't be moving left and right. And we know on my red null line, I must be moving left or right. I can't be moving up or down. That helps me make sure I don't accidentally put my arrows on the wrong axes. So whenever we're doing this direction field, we're looking, say, on our null lines, we're actually going to be looking at n1 is equal to 0. So we're going to be looking at this one and this one first. What we're doing is we're saying, okay, I'm stood at, say, a point on this null line here. I know that I can't be moving left or right because dn1 dt is equal to 0. And I want to know, am I moving up or down? Likewise, what happens if I go through an equilibrium down here? Am I moving up or down? Okay, so I'm stood on this line n1 is equal to 0. I know I can't be moving left or right. I want to know, am I moving up or down? So all I do is I substitute this equation here, whatever it is, into this equation for dn2 dt. So we know dn2 dt is equal to n2. That's by 1 minus n2 plus n1 over 2. Now here you might have an equation for n1 and n2 that you're substituting in, and here you'll be eliminating one of these variables. In this case, there's just an n1. We know n1 is equal to 0, so we can eliminate this n1 here. So we have dn2 dt is equal to n2 plus by 1 minus n2. And what we care about is when is dn2 dt positive and when is it negative, depending on the variables on the right-hand side. So what can we say? Well, dn2 dt is going to be positive if n2 is positive and it's less than 1. This will give us arrows moving up. And it's going to be negative. Well, it's going to be negative if n2 is negative, but we've got population sizes here. So we can't have negative population sizes. We don't care about what's going on if n2 is negative. But if n2 is greater than 1, then dn2 dt is going to be negative. So let's go back up to this diagram here. That means if n2 is greater than 1 and we're on this line n1 is equal to 0, we must be moving down. And if we're between 0 and 1, we're going to be moving up. Now you can work through the second one as well in your own time if you want to. Because this is symmetric, I know it's going to be exactly the same on the other side. If I flipped all my N1s and N2s around, nothing changes, okay? So in this particular case, I know that this is going to be an arrow going this way, and this is an arrow going this way. Yeah, this is because the system is perfectly symmetrical. Okay. Another little tip and trick we can do at this point is if we know what's going on these null lines here, we only change direction as we go through a fixed point, okay? So that means imagine if I zoom in here and I step a tiny little bit off this axis here, I'm still going to be moving mostly down. I'll also be moving a little bit left or right because we're no longer on a null line, but I'm not moving up. I know I'm going to be moving down in some direction. Likewise here, if I step a little bit away from the origin here, I know I have to be moving up, but I also have to be moving to the right. Okay, so in this case, I don't actually have to worry about working out what my arrows are doing on these null lines and working out the individual direction field. Because these are continuous functions, if you move a little bit, you're not suddenly going to change direction unless you go through an equilibrium. So that means I know in this region here, well, actually, let's start in this region because this region is going to be the easiest. I'm going to have to be going up and to the right. Okay. So that tells me that these arrows here must be going to the right, and these ones also have to be going up. In this region here, up the top, I know I'm moving down because I'm moving down on the axis, and I have these red arrows moving to the right, so I know I'm moving down and to the right, so I'm moving in somewhere in this direction. Whereas these arrows up here must be down because the ones on the axis are down. So over in this, let's do this bottom right quadrant here. I know I have to be moving to the left, and I'm also moving up because of these arrows here and here. So actually moving in this direction. That leaves me one more quadrant here. Because I'm moving to the left below, I must still be moving to the left because I've not gone through a fixed point here. So in this region up here, I know I must be moving down and to the left. So you don't necessarily have to work through every single combination of things on your null lines. I didn't have to actually work out what all of these arrows were on my non-zero null lines. I could just do it by deduction. So if this was in an exam, I would allow it as long as you get the right answer. The only problem with doing this is that you don't leave any of your workings there. I have workings here for this one null line, and then I basically deduced everything else. That is a little bit of a risky thing to do. I would give full marks for this if you got it correct, okay? But just be aware that if you do that process of deduction, you are leaving yourself a little bit open because you haven't shown any working. So it is correct, and I would give you full marks for this, but just be aware of the slight consequences of doing that. Okay. Of course, you can always check these by substituting them in. Okay. So if we draw some trajectories here, we see that if we start at a non-zero value for N1 and N2, we tend towards this coexistence equilibrium here. We'd already worked out that this was a stable node, but we can see it from our phase plane as well. And this was the point 2, 2. Okay, any questions? Okay, for the last few minutes, I'm just going to go through a general version of this model. Okay, so before we had A was equal to a half and B was equal to a half, but we could just think about a general form of this model where we have parameters, positive parameters A and B. So we don't know what these are, and we can work out what goes on in this case. So I'll leave working out the fixed points as an exercise. I mentioned we can turn this into a linear system to work out our fixed points for our coexistence equilibrium. It turns out that if it exists, we have, my pen's died. There we go. If it exists, we have N1, N2 is equal to 1 plus A, 1 plus B, and both of these over 1 minus AB. Okay, so there's the answer, and try and work towards that if you can. You're in time. Crucially, this is only going to be biologically realistic. The numerators are always positive. The denominators are only positive if A times by B is less than 1. So this coexistence equilibrium only exists if AB is less than 1. So we can think about two possibilities now. We can think about the possibility of what happens if AB is less than 1. What's our phase plane going to look like? So you can have a go at sketching this. We've actually already got this case up here. Because our A was equal to a half and our B was equal to a half that we've, in the example that we've just been through, AB was less than 1. So our phase plane ends up basically looking like this. Okay. The location of that fixed point will vary as A and B varies, but qualitatively it looks like this. Again, you can have a go at sketching the general form. Let's think about the other example here if AB is greater than 1. So if AB is greater than 1, we have no coexistence equilibrium. So what does that mean? Well, let's draw on our null lines that we know about. We know that we're always going to have one here on my N2 axis, and have one here on my N1 axis that we had previously. We know that we don't have a coexistence equilibrium. So that means that the null lines can't intersect. I see you dividing the C's there. That's basically what's going on here. Okay, they can't intersect. What does that mean? Well, I know I have to go through, I'll still have to go through 1, 0 here. And this one, I have to go like this. What it means is these lines are diverging. They never intersect in this positive quadrant. If they intersected, you'd have something right over here. These lines would have to intersect somewhere, right? So they can't intersect. If they intersect, then we have a coexistence equilibrium, but we know that we don't have a coexistence equilibrium. So we know that my null lines have to look like this. We can also deduce what we had from our previous diagram. So on a previous diagram, we had these arrows on our axes pointing in these directions here. And just like I did on the previous diagram, I can think about what happens if I move a tiny bit away from the axis in any of these directions. I'm going to move a little bit away from the origin here. I know that I must be moving up and to the right because that's what's going on the axes. So that means in this middle block here, I must be moving up and to the right. About in the top left, that little triangle above the red line. Well, I know I still must be moving to the right. I'll also be moving down. So here I know I'll be moving down and to the right. In this bottom triangle below the blue line, I know I must be moving left. And because the arrow over here is moving up, this arrow has to be moving up. I'll be moving to the left. So in this region, I'm moving up and to the left. That's all I need to tell me what's going on here. If I start at any non-zero values for N1 and N2, suppose I start over here, I'm going to start by moving down and to the left, across the null line, horizontally going to the right, and then I'm moving up and to the right, and I just keep going in that direction. Likewise here, I'm moving up and to the left, and keep going off infinity. So what this means is that these populations, there's a positive feedback between them, and they keep growing and growing and growing, and they go off to infinity, which isn't very realistic, but it means that there's a positive feedback between these populations. There's no coexistence equilibrium, everything just goes off to infinity. Okay, so this is saying something about what is the strength of this mutualism between these species. If it's stronger than the intraspecific effects, then everything blows up. Okay, I'll see you on Wednesday.